So, welcome to lecture number 36 of our discussion of fundamentals of transport processes. In the last few lectures, we first derived the convection diffusion equation in different coordinate systems. That equation had the general form dc by dt plus del dot u c is equal to d del square c plus any sources or sinks that are present within the flow. And I showed you that if you scale the velocities is equal to u by capital U and all distance x by some characteristic distance L, the radius of a particle, if a particle is immersed within the flow, or the pipe diameter if this flow through a pipe. The time scale becomes t is equal to t d by L square. In that case, you get a dimensionless equation of the form P e into dc star by dt plus divergence of u c is equal to d del square c plus the source. Let me just remove this. So, this is what you get, and there is this Peclet number sitting out in front here, which is basically P e is equal to u L by t. So far, we have been considering the limit of low Peclet number. We have been considering which implies that del square the equation reduces to d del square c plus source is equal to 0. So, we looked at some general strategies to solve this problem. D del square c plus any source or sink within the flow is equal to 0. Basically, it is general strategies for solving del square c is equal to 0. That is, the Laplacian of the concentration field is equal to 0. And we looked at different ways of solving this. Separation of variables as well as solution strategies based upon considering a point source within the flow, and then considering a distributed source as the summation of many small point sources. Here we are going to start looking at the opposite limit, where the Peclet number is large compared to 1. Simplistically, you would think that we can just go ahead and solve it by using the equation dc by dt plus divergence of u c is equal to 0. However, that is not so, and I will try to explain to you why that is not so by considering first the simplest case, which is the flow past a flat plate. We consider solution of the conduction equation in the flow past a flat plate. So, I have a flat plate here, and T is equal to 0, and at a particular location the temperature is instantaneously increased to a higher value. So, T is equal to T1. So, let us just, rather than 0, let us just write this as T naught. So, at this particular location you are starting to heat the fluid, and the flow near the fluid is a linear velocity profile. The flow in the near the surface is a linear velocity profile u. and the temperature of the fluid that is entering is basically at the same temperature as this unheated section, T is equal to T naught. Okay. Consider, for example, a heat exchanger problem where I have heat coming in at the inlet. I have a cold fluid coming in at the inlet, and at one particular location it comes into contact with the heated fluid outside, okay, because the wall at that particular location is heated. So, I have cold fluid which is initially coming in at temperature T naught. At one particular location I start heating. I set the temperature is equal to T 1 at the wall of the tube itself. Rather than considering a cylindrical surface, I will just consider a flat plate. So, let us first write down our coordinate system. Okay. I will use x as the coordinate along the flow, y as the coordinate perpendicular to the flow. Okay. The velocity field, the velocity is only in the x direction, parallel to the flat plate. Okay. So, the velocity u x is linear function of y, okay. It increases linear as y increases. I write it as gamma dot times y, where gamma dot is equal to the strain rate, okay, where gamma dot is equal to the strain rate. Okay. And let us consider that this process is happening at steady state, okay, so that there is no time derivative. Okay. So, my heat conduction equation just becomes partial del dot u c is equal to alpha del square, so this t. Alpha del square t. Okay. So, this is the equation that I am going to try to solve within this domain, okay, in the limit of high Peclet number. Okay. Now, what does high Peclet number mean, okay, in this case? Okay. So, let us consider that this heated section has a length L. Okay. So, length L is the heated section, okay, the length of the heated section. Okay. What does high Peclet number mean? I have a thermal diffusion coefficient alpha, dimensions length square per unit time. Okay. I have a characteristic length which is the length of this heated section L, okay, characteristic length in the problem, and there is no velocity scale, but there is a scale for the strain rate. U x is equal to gamma dot times y. Okay. So, the strain rate gamma dot has dimensions of inverse time, because velocity is length per unit time is equal to gamma dot times the length. Therefore, the strain rate has dimensions of inverse time. That means that I can create a dimensionless number, okay, which is the ratio of convection and diffusion as Peclet number is equal to gamma dot L square by alpha. So, this gives me the ratio of convection and diffusion in this particular case. Okay. So, this gives me the ratio of convection and diffusion in this particular case. Further, the velocity is not varying as a function of the streamwise direction. Okay. So, I have u x is independent of y, I am sorry, independent of x, and u y is equal to 0. There is no flow perpendicular to the plate. Okay. So, u x is independent of x and u y there is no flow perpendicular to the plate. Okay. So, with this my conservation equation would become u x partial t by partial x. Okay. U x is independent of x. So, I can take it out of the differentiation, plus u y times partial t by partial y, but u y is equal to 0, okay, is equal to alpha into partial square t by partial x square plus partial square t by partial y square. So, this is the convection diffusion equation for the steady case where there is a velocity only in the x direction. Okay. So, now I scale, okay. U x is equal to gamma dot times y partial t by partial x is equal to alpha partial square t by partial x square plus and I have a length scale. Okay. So, I can scale all lengths, scale x star is equal to x by L and y star is equal to y by L. Once you do that, you will get gamma dot L square by alpha y star dt by dx star is equal to d square t by dx star square plus d square t dy star square. Okay. So, that is the differential equation in scaled form. Okay. Further, I should scale the temperature as well. Okay. I can define a scaled temperature T star is equal to T minus T naught by T 1 minus T naught, okay. In which case T star is equal to 1 here and T star is equal to 0. Okay. So, in terms of the scale temperature, since the equation is linear in the temperature anyway, okay, if I write it in terms of the scale temperature, I will just get P E y star d t star by dx star is equal to d square t by dx square plus okay. So, this is the equation that I get with boundary conditions. T star is equal to 1 at y is equal to 0 for x greater than 0. So, for x greater than 0, I have the heated section of the plate where T star is equal to 1. Okay. So, T star is equal to 1 on this heated section of the plate in the at y is equal to 0, okay, for x greater than 0 of course. Okay. As I go far from the plate, the temperature should be equal to this free stream temperature. Okay. If I go very far from the plate, as y goes to infinity, I should recover T star is equal to 0, right, because the effect of heating from the plate has not yet reached that far. So, as y goes to infinity, T star has to decrease to 0. And T star is equal to 0 as y star goes to infinity. Okay. In addition, fluid that is incident on the plate for x less than 0, it has not been heated yet. Okay. Fluid that is incident on the plate for on the heated section, for x less than 0, it has not yet been heated. So, therefore, for x less than 0, for any value of y greater than 0, the temperature should be equal to 0. Okay. So, that is the initial condition, okay, for the fluid that is incident on this heated section. Okay. Therefore, I require that T star is equal to 0 at the location x is equal to 0, because it has not yet touched the heated section of the plate for y greater than 0. Y is equal to 0 is heated, but anywhere above is not yet heated. Okay. So, the temperature should be 0 for all locations y greater than 0. So, we have to solve this equation subject to these boundary conditions. In the limit where the Peclet number is large. So, that we would expect convection to be dominant in comparison to diffusion. Okay. So, simplistically, okay, we just neglect diffusion, okay, and we will end up with an equation of the form dt star by dx star is equal to 0. Okay, because if I neglect diffusion, then I just get P E y star times dt by dx is equal to 0, and if y is non-zero and Peclet number is non-zero, then dt by dx has to be equal to 0. Okay. That means that the temperature is invariant in the x direction. Okay. The temperature is independent of x. Okay. The temperature is independent of x. Okay. It depends only upon the y coordinate. Okay. However, that means that if dt star by dx star is equal to 0, this condition tells us that t is equal to 0 for all y at x is equal to 0. Okay. Basically, what dt dx is equal to 0 tells you that there is no variation along the flow streamlines of the temperature. However, at the inlet the temperature was equal to 0 independent of position. That means that the only solution is T star is equal to 0 everywhere. Okay. Since T is independent of x, okay, at the inlet T was equal to 0 everywhere, therefore, the value has to be constant at all values of x. At the inlet it was equal to 0, therefore, at all values of x as you go downstream the temperature has to be identically equal to 0. So, that is the solution that you get in the high Peclet number limit. Okay. There is no diffusion. So, because of that there is no transport across streamlines. Okay. There is no transport across streamlines, and because of that whatever temperature was there at the inlet continues to be the same temperature everywhere within the flow. At the inlet the temperature was 0. So, everywhere within the flow the temperature continues to be 0. Clearly, this solution is not compatible with this boundary condition, that in the heated section T is equal to 1. Okay. Clearly, it is not compatible with this boundary condition. Okay. What this solution is saying, if you neglect diffusion altogether, the temperature continues to be a constant and there is no effect of heating in that heated section. Okay. So, it is incompatible with one of the boundary conditions. The mathematical reason for this incompatibility is quite obvious. Okay. If I neglect the diffusion terms altogether, the diffusion terms had the second derivative with respect to the y coordinate. Okay. The diffusion term had the second derivative with respect to the y coordinate. That second derivative, because it was a second order differential equation in y, I had two boundary conditions in y. When I neglected that diffusion term, the second order term in y, I converted this from a second order differential equation to an ordinary equation in y. So, with an ordinary equation one cannot satisfy any boundary conditions. That is the reason that we are not able to get satisfy the boundary conditions at the surface of the plate, because when we neglected the diffusion terms, we have neglected the highest derivative. Okay. And once you neglect the highest derivative, you can no longer satisfy all the required boundary conditions. So, that is the mathematical reason why we are not able to satisfy boundary conditions. The physical reason is, as I have been telling you numerous times during the course of these lectures, convection transports mass, momentum and energy only along the flow direction. Transport across streamlines can take place only due to diffusion, because convective transport takes place only along the flow direction. Diffusion has to take place perpendicular to the flow direction. When I neglect diffusion in comparison to convection, there is no transport across streamlines. Okay. However, if you look at the mean velocity itself, at a bounding surface, the mean velocity has to be 0 from the no slip condition and from the no penetration condition. There can be no flow perpendicular to the surface at a surface, because at the surface itself, the velocity of the surface has to be equal to the velocity of the fluid. So, there is no relative velocity between the fluid and the surface at the surface itself. So, there is no relative motion between the fluid and the surface, and because of that there can be no net transport perpendicular to the surface due to convection. Any transport perpendicular to the surface has to ultimately take place only due to diffusion. Okay. So, because of this physical reason, because we have neglected diffusion perpendicular to the surface, there is no transport of heat, and consequently there is no heating up, change in temperature due to the heated section due to when we neglect the diffusion terms. However, diffusion is still present. It is a molecular phenomenon and it is going to exist. It may be small, but it is still going to exist. Okay. So, how does one bring diffusion into this problem? Okay. And the key basically lies here. Okay. Note that this condition says that T star is equal to 0 at x star is equal to 0 for y greater than 0. Okay. Note this condition, it says for y greater than 0. Okay. Because at the surface itself there is 0 velocity, the velocity is equal to 0 exactly at the surface. So, there is no transport along the surface. So, for y greater than 0, T has to be equal to 0. This other boundary conditions that says that T star is equal to 1 exactly at y is equal to 0. Okay. So, if I plotted the temperature field due to this, okay, if I plotted as a function of y, if I plotted the temperature, at the surface itself the temperature has to be 1, okay, but everywhere above it has to be equal to 0. Okay. That is what the diffusion equation or the convection diffusion equation is saying without the diffusion terms. Okay. However, a profile like this is step profile. Okay. If you have a step profile, the derivative of a step function is a delta function which goes to infinity. Okay. So, if I have a step profile, the derivative is actually very large. Okay. So, even though the Peclet number may be large, okay, and even though I have an equation of the kind, okay, gamma dot y dt by dx is equal to 1 by P e times d square t by dx square plus d square t by dy square. Okay. Even though this prefactor may be small, because the Peclet number is large, if the derivative is large, okay, the product of these two could still be comparable to the convection term. Okay, the product of these two could still be comparable to the convection term. Okay. Note that when I did the scaling here, okay, I implicitly assumed that y star is equal to y divided by L. That means the length scale for variation of temperature in the y direction is equal to L. Okay. So, when I did the scaling in this manner, I have implicitly assumed that L is the length scale over which the temperature varies in the y direction. On that basis, I did my scaling, and then I found out that convection was large compared to diffusion, and therefore, I tried to neglect the diffusion term. Okay. However, if the length scale for diffusion is smaller than L, if the length scale for diffusion is smaller than L, then the gradients will be larger, okay, because the derivative goes as the temperature difference divided by the length scale of variation. So, if the length scale is smaller, the gradient could be much larger, and if the length scale is sufficiently small, I could still get a balance between convection and diffusion, even though the Peclet number based upon capital L is large. Okay. I could have a smaller length scale over which there is diffusion, such that the gradient is sufficiently large that there is a balance between convection and diffusion. That is what is actually happening in high Peclet number flows. Okay. Very near the surface, diffusion has to exist, because that is the only way the fluid is going to get heated. Okay. But however, if I go a length scale comparable to L from the surface, my balance between convection and diffusion tells me that convection has to be dominant. If I go a distance L away from the surface, okay, diffusion could still be important within a much smaller length scale. Okay. Because convection is so fast, the heat will not penetrate very far into the fluid, but diffusion will still be important over a much smaller length scale. Okay. And that length scale is determined in such a way, or has a sufficient value that over a distance comparable to that, there is a balance between convection and diffusion. Okay. So, how am I going to solve this problem? I said physically the reason that we are not able to get a balance is because we have assumed that the length scale for variation in the y direction is capital L. If the length scale for variation in the y direction were much smaller than capital L, there might be a balance between convection and diffusion. Okay. What should that length scale be? Okay. So, what I will do now is to just write down scaling x star is equal to x by L. This is usual. This is the length scale for variation of temperature along the x direction, because the heated section has length capital L. Okay. However, in the y direction I will postulate a smaller length scale, small l, okay, and then go back and scale my equations once again. So, my original equation was gamma dot y partial t by partial x is equal to d into partial square t by partial x square plus partial square t by partial y square. This should be the thermal diffusivity alpha. Okay. Okay. And with this scaling, as well as with T star is equal to T minus T naught by T 1 minus T naught, okay, this becomes gamma dot L y star by capital L partial T by partial x is equal to alpha into 1 over L square So, this now is my convection diffusion equation with y scaled by as yet unknown length scale small l. Okay. Note that within this equation, okay, in the diffusion terms, this one contains a prefactor 1 over small l square. The first term contains a prefactor 1 over capital L square. We had postulated that small l was small compared to capital L. That means that this diffusion term in the y direction is large compared to the diffusion term in the x direction, okay, because the diffusion term in the y direction goes as 1 over small l square. The diffusion term in the x direction goes as 1 over capital L square. That means that this second diffusion term in the y direction, the cross stream direction, is large compared to the streamwise diffusion. So, I divide throughout by alpha by L the whole square. Okay. If I divide throughout by alpha by L the whole square, okay, or rather in the limit of high Peclet number I should divide by this term, divide throughout. Okay. The equation becomes y star dt by dx is equal to alpha L by L comma dot into 1 over L square partial square T by partial y square plus 1 over L square okay. Alternatively, I can write this as alpha L by L cubed comma dot into okay. So, this then is my convection diffusion equation. Okay. Note that this is a small number. Okay. This is a small number because I postulated that small l is small compared to capital L. Okay. Therefore, I can neglect streamwise diffusion in comparison to cross stream diffusion. Okay. And if I do that, what I will get is that y star partial t by partial x is equal to alpha L by L cubed comma dot partial square t by partial y square. Okay. Now, this is the convection diffusion equation, and if convection and diffusion have to be comparable in the high Peclet number limit, it means that this term here has to be of order 1 in the high Peclet number limit. Okay. If convection and diffusion are to be comparable in the limit of high Peclet number, I require that this term has to be order 1. Okay. That means that L cubed comma dot by alpha L is 1, okay, which means that L by L the whole cubed is equal to alpha by comma dot L square. Okay. Okay. Now, alpha by gamma dot L square was the original Peclet number that I had inverse, okay, because if you recall, we defined the Peclet number as is equal to gamma dot L square by alpha for this problem. Okay. So, therefore, I require that L by L is equal to P e power minus 1/3. Okay. So, what this is telling me is that in the limit as the Peclet number becomes large, there is a length scale a length very near the surface small l, over which diffusion is comparable to convection, and that value of small l decreases as P e power minus 1/3 in the limit as the Peclet number becomes large. Okay. I said that this term has to be just order 1, okay, and but however, I can set it equal to 1 without loss of generality, because it is just a length scale, okay, which I am obtaining by scaling. Okay. I can set it equal to any constant value. It will change the equations in terms of the length scale L, but when I get the final solution for the physical problem, there will be no dependence on this constant. So, without loss of generality, I can set this constant just equal to 1. Okay. So, this is what is called the boundary layer thickness, okay, the thickness of the region over which there is a balance between convection and diffusion, even when the Peclet number is large. It's for this reason that I said, even when the Peclet number is large, even though it appears that convection is dominant, is large compared to diffusion, there is still going to be a region very close to a surface where diffusion is present, and it is comparable to convection. That is because the transport from a surface cannot take place due to convection, because there is no velocity normal to the surface. Diffusion, on the other hand, is an isotropic process. It is due to the fluctuating velocities of the molecules, which have equal magnitudes in all directions, and therefore, they transport mass, momentum and energy equally in all directions. Therefore, very close to the surface, even though convection is not present, there is still diffusion, and that diffusion is what causes transport from the surface itself. And the variation of concentration very close to the surface has a length scale L, which is determined from the requirement that convection and diffusion have to be comparable very close to the surface. This requirement itself gives us what is the value of the length scale. In the limit as p goes to infinity, okay, as the Peclet number becomes large, this length scale goes as p power minus 1/3, okay, in the limit as the Peclet number becomes large. And as we saw just now in this equation, streamwise diffusion is always small compared to the cross stream diffusion very close to the surface, because the length scale for cross stream diffusion is the small l, which goes as p power minus 1/3. The length scale for streamwise diffusion is the macroscopic scale capital L itself. Therefore, for this particular problem, okay, the convection diffusion equation reduces to gamma dot y dt by dx is equal to alpha d square t by dy square. Okay. You can write in terms of the scaled coordinates. Okay. For this particular problem, this is the equation. We can neglect the streamwise diffusion in comparison to the cross stream diffusion. Now, we obtained, based upon scaling, we obtained this as the simplified equation. How do we solve this? This is still a partial differential equation which contains variations both in x and in y. Okay. The solution procedure for this simplified equation is we can formulate a solution procedure based upon our physical understanding of this problem. Okay. So, I have this section, and then I have a heated section here. Okay. So, this is y, this is x, okay, and this heated section has some length L. Okay. The flow is incident on this heated section. Okay. So, T is equal to T naught here, or T star is equal to 0, T star is equal to 0, and T star is equal to 1. Okay. And we are considering the limit where convection is dominant comparison to diffusion. Okay. And on that basis, we said that there will be some boundary layer length here, okay, of length small l, okay, which goes as L times P e power minus 1/3, over which there is a balance between convection and diffusion. Okay. However, if you consider, for example, any particular location, okay, if you consider any particular location, okay, x, okay, if I consider any particular location x, I have diffusion coming out of the surface, okay, diffusion of heat is coming out of the surface, okay, and there is convection. Now, convection is taking the energy downstream, okay. Convection is taking the energy downstream, and we are considering the case where convection is large compared to diffusion based upon the length L. So, convection is taking the energy downstream, there is diffusion from the surface. That means that at a given position x, the temperature should not depend upon the total length L, because that total length L is downstream of the position x. Okay. So, the temperature at a given location x cannot depend upon the total length L downstream of that location. It should depend only upon the length of the heated section up to that particular location x. Okay. It should depend only upon the length of the heated section up to that particular location x. Okay. That means that the only length scale on which this temperature at a given location x should depend is on the distance x from the start of the heated section itself, not the total length of the heated section. because the total the remainder of the heated section is downstream of this position, and flow is carrying the heat downstream. Okay. So, there can be no diffusion in the streamwise direction, which basically enables the temperature at this location x to feel the downstream locations. Okay. So, if x is the only length scale in the problem, then the boundary layer thickness L at a given location x divided by x has to be equal to the Peclet number based upon x to the minus 1/3, which is equal to alpha by gamma dot x square power 1/3. Okay. So, the only length scale in the problem is x. So, I have just substituted x for L in this particular case, and I have assumed that the boundary layer thickness itself is a function of x. Okay. This will enable us to get a similarity solution, because if the length scale in the y direction is L, then I can define a scaled similarity variable as y by L of x. Okay. And L of x is equal to alpha x by gamma dot power 1/3. If I can define this as y by alpha x by gamma dot power 1/3. Okay. This was obtained just basically from the consideration that at a given location x, the temperature should depend only upon the distance from the start of the heating section, not the total length of the plate itself. So, I cannot scale my y coordinate, the boundary layer thickness, by capital L, because at a given location x, it should not depend upon the total length L. It should depend only upon the distance x from the upstream section. So, my boundary layer thickness L of x has to be alpha x by gamma dot power 1/3. If this is the boundary layer thickness, then I just divide y by that to get a scaled variable, okay, because the characteristic length scale in the y direction is this small l. Okay. So, I can define eta is equal to y by alpha x by gamma dot power 1/3. This is the similarity variable which will reduce the problem from 2 dimensions to 1 dimension. If you recall the impulsively started plate, okay, there we had obtained a similarity solution based upon dimensional analysis, the fact that there is no length scale or time scale in the problem, therefore, I can get only one similarity variable. Here we are doing this based upon physical insight. Okay. So, now I have to substitute in this convection diffusion equation. Okay. I have the convection diffusion equation gamma dot y partial t by partial x is equal to alpha partial square t by partial y square. Okay. So, in this equation I have to substitute y and x in terms of eta. Okay. So, I will get partial t by partial y is equal to partial t by partial eta times partial eta by partial y is equal to 1 over alpha x by gamma dot power 1/3 partial t by partial eta. Okay. D square t by dy square is in a similar manner 1 over alpha x by gamma dot power 2/3. Okay. And dt by dx is equal to dt by d eta times d eta by dx is equal to y by power 1/3. Okay. X power minus 1/3, the derivative gives you minus 1 by 3 times x power 4 by 3. Okay. So, this finally has to be substituted into this differential equation. Okay. And then we have to get a solution for this differential equation. Okay. If what we have done here is correct, then when I substitute this into that differential equation, I will end up with an equation in terms of eta alone. It should not depend separately on x and y. The final equation should depend upon eta alone. Okay. So, what do you get when you substitute this? Okay. You get gamma dot y into minus y by 3 x alpha x by gamma dot or 1/3 dt by d eta is equal to alpha into divided by alpha x by gamma dot or 2/3 d square t by d eta square. Okay. So, I can simplify this a little bit, okay, by using the simplification y is equal to eta into alpha x by gamma dot power 1/3. Okay. So, I will get gamma dot eta square into alpha x by gamma dot power 1/3 by 3 x into alpha x by gamma dot power 1/3 okay, dt by d eta is equal to alpha by should have 2/3 here. Or 2/3 d square t by d eta square. Okay. And you can easily verify that all of these terms will cancel out finally to give you minus eta square dt by d eta is equal to d square t by d eta square. Okay. So, this then is the final solution, okay, for the equation in terms of eta. Okay. As we had expected, if we scaled the y coordinate by that length L, which is based upon the x distance, the distance from the upstream edge, okay, then you will finally end up with a solution in which it does not individually depend upon x, y, gamma dot and alpha. It depends only upon the similarity variable eta. Okay. So, this gives us a solution for the temperature field in terms of the similarity variable alone. Okay. And does not depend separately on x and alpha on y and x, but only on the similarity variable alone. Okay. So, now we have equations in terms of the similarity variable eta. Okay. We have to reformulate our boundary conditions as well in terms of the similarity variable eta. Okay. The original boundary conditions, okay, at y is equal to 0, t star is equal to 1. T star is equal to 1 at y is equal to 0 implies that eta is equal to 0, because eta is equal to y by alpha x by gamma dot x by alpha power 1/3. Okay. As y goes to infinity, t star is equal to 0. Y going to infinity implies that okay, this implies that eta is going to infinity. Okay. And at x is equal to 0 for y greater than 0, t star is equal to 0. And you can see from this that x is equal to 0 basically means that eta goes to infinity. Okay, x is equal to 0 basically means that eta goes to infinity. So, at x is equal to 0, so you can see that both of these boundary conditions, one boundary condition in the y coordinate as y goes to infinity and the other in the x coordinate at x is equal to 0, reduce to the same boundary condition when expressed in terms of eta. Okay, these two reduce to exactly the same when expressed in terms of eta. That is expected. Originally, I had a first order differential equation in x and a second order differential equation in y shown in red right on top there. Okay. It was first order in x, second order in y. I need two conditions in y and one in x. When I reduced it using a similarity transform, I got only one second order equation in eta itself. It has only two boundary conditions. That means that one of the boundary conditions in y as well as the initial condition in x has to reduce to the same when expressed in terms of eta. Okay. So, I can solve this equation minus eta square partial t by partial eta is equal to partial square t by partial eta square. Okay. Integrate it once to get partial t by partial eta is equal to e power minus eta cubed by 3. Okay. I integrated once to get partial t by partial eta is equal to c, I am sorry, there is some constant here, c1 e power minus eta cubed by 3, and I can integrate this a second time to get t star is equal to integral, okay, from 0 to some value of eta, eta prime exponent of minus eta prime cubed by 3 plus some other constant C2. Okay. So, this is the final solution. Okay. So, this integral cannot be evaluated exactly. Okay. So, because of the because we have a definite integral here, because we cannot integrate e power minus eta cubed by 3 exactly. Okay. And then we apply the boundary conditions. Okay. T star is equal to 0 as eta goes to infinity and t star is equal to 1 at eta is equal to 0, in order to determine, specify the constants C1 and C2. Okay. So, the constants turn out to be this final solution after imposing the boundary conditions turns out to be eta prime e power minus eta prime cubed by 3 divided by integral 0 to infinity you can easily verify that this solution is 1 at eta is equal to 0 and it is 0 as eta goes to infinity. Okay. So, this is the final solution for the temperature field in terms of the variable eta, where eta is equal to y by alpha x by gamma dot power 1/3. Okay. So, there is a final expression in terms of this eta. How can we use this to calculate the heat flux? Okay. The total amount of heat coming out of the heated surface. Locally, the heat flux Qy is equal to minus k dt by dy. Okay. I have to express this in terms of eta. Okay. So, if you recall, dt by dy is equal to 1 by alpha x by gamma dot power 1/3 times dt by d eta. Okay. Okay. the heat flux coming out of the surface is at y is equal to 0. So, this will be equal to minus k by alpha x by gamma dot power 1/3 dt by d eta at eta is equal to 0. And dt by d eta at eta is equal to 0 can be quite easily calculated from this solution here. Okay. From this solution here, dt by d eta is just equal to minus okay. So, this q y will be equal to minus k by alpha x by gamma dot power 1/3 into minus 1 by integral 0 to infinity d eta prime e power minus eta prime cube by 3 okay. Into okay, T1 minus T0 okay, because T is equal to T1 minus T0, T minus T0 by T1 minus T0 times T star. Okay. So, this is the final expression we get for the heat flux. Okay. So, this is equal to k into T1 minus T0 by alpha x by gamma dot power 1/3 times this function can be integrated exactly. It gives you gamma of 1 by 3 by 3 power 2/3. Okay, so, that is the final solution for the heat flux from the surface. Okay. The average heat coming out of the surface, okay, the average heat coming out of the surface is an average over the entire length integral 0 to L dx times q y at each location x. Okay. And this can be evaluated analytically okay, in order to get the average heat that is coming out of the surface. From this, we will now go ahead and calculate the Nusselt number correlation for the heat transfer from the surface in the limit of high Peclet number. When we did the initial lectures, I showed you that the Nusselt number in the case of convection dominated flows at high Peclet number goes as P e power plus 1/3. We have done here an analytical solution for the flow past a flat surface at high Peclet numbers, and we have got a solution in terms of the similarity variable. I will now use this to show you how we get the high Nusselt number correlations. So, we will first complete the solution of flow past a flat plate in the next lecture, and then I will discuss the flow past a spherical particle and evaluate the Nusselt number correlation in that case. So, slowly we are recovering all those original results that we had as empirical correlations, the same thing we are deriving here by an exact relation, by exact calculations using certain approximations, the low Nusselt number limit and the in the low Peclet number limit and the high Peclet number limit. We will continue this in the next lecture. We will see you then.